Okay. Right, so what I was planning to do was to try and give you an overview of what a Kuranishi structure is for a space and how we get, what we're aiming to do. We've got this space X, which is going to be compact and metrizable. And I'm going to put on it some Kuranishi structure. K is a Kuranishi structure. And then the aim is to define some homology class, which is actually going to be, I realize the right homology is the Czech homology, rational Czech homology. So it's some homology class in there which is well defined up to some notion of cobordism, which I will explain, and that will be the virtual fundamental cycle. So that's our aim to do that.
Can I say one more?
Mm-hmm.
Actually, that's not what Fuka and Ono did. What they do is construct using this Kuranishi space to construct some cycle in the target.
Yes, I know, but I mean it's actually neater to construct something in the domain, because of course if you've got an evaluation map, this will map to the target. And this Czech homology, if you have a reasonable space, it's the same as ordinary homology. It's just we don't know anything about X, and Czech homology has got a certain, it has a continuity property that if you've got X, you've got some open subsets, some nice finite CW complex kind of spaces, and you've got a nested sequence of these, and you've got X being the intersection of all these things, then you get an inverse limit of, you've got some consistent set of classes in here. So you've got CI in Czech homology of the UIs, which behave well under these maps, so that CI plus 1 goes to CI. Then you get some inverse limit, and this element is a well-defined thing in X. That'll give you, this inverse limit of the CIs does give you something in the Czech homology of X. And that's a particular kind of homology which has this continuity property which normal, ordinary singular homology doesn't. But, this is equal to ordinary homology for all nice spaces, and so it's just a neat way. In fact, I learnt this from Alexei, who constructed a pseudo-cycle in the moduli space. That's a sort of neat way. When you were doing that pseudo-cycle paper, you constructed it in the space of, you were trying to show that the Gromov-Witten, the space of non-compact space was a pseudo-cycle, and you constructed it you constructed a homology class in the space of maps itself.
Yes, but not homology.
Well, they were, anyway, these are in the space X itself. You can make something. So I need to give you definitions, and I'm going to just essentially do the topological part of this theory. So I'm assuming everything is smooth, no worries about gluing, everything is sort of nice. And I first want to tell you what a Kuranishi structure is. So we have to start with the Kuranishi chart. Oh yeah, and the other thing I should say is that I'm going to restrict to no isotropy. So again, just to keep things really easy, there are no, we don't have finite automorphism groups. So you can say none of our curves are multiply covered. There's no reason to have any automorphism. So a Kuranishi chart, well, this is exactly what Fukaya and Ono say. It's some open subset. It's a tuple consisting of, I'll just write it down, U, S, S, and psi. And U is sitting inside some Euclidean space. It's open subset. E is a finite dimensional vector space. And so the bundle that we're interested in, we think we have a bundle, is just U cross E over U. So we have a finite dimensional bundle that we've chosen, which trivialized. So that's our fiber of our bundle. S is a section here. So S we can think of as a map from U to E, smooth, which is the Del-Bar operator or whatever you're trying to model. And then what we're interested in is the 0 set of S. And this is going to be identified. Psi is going to be a map from this into X. And the image here, it's going to be, its image is F. So this is image of psi. And this is what we call the footprint of the chart. And so that's an open subset. And that's the essential data of the chart. That's the important thing about the chart. U is what we call a domain. And that, of course, we're interested in only insofar as it contains a footprint. But we do always fix a domain. But there's always a choice of domain. That's one of the things. I mean, we can't, the only thing the only bit of the chart that we can't move around is the footprint, or if we do that, we're really changing the chart.
In particular, there's a choice of notation for the domain, because I call it B.
Yeah, okay. Well, and we may have had slightly different choices. I mean, E now is a vector space. It's not a bundle, it's a vector space. My bundle is U times E over U. S is our del bar operator, and psi is our footprint map. Yes, I should have said. This is a homeomorphism to its image, right?
And you assume that the footprint is open.
I assume that the footprint is open, right? Yeah, it's part of the hypothesis. Okay, so then we have a natural operation of restriction, which would, so it took us a long time to work this out, but as I say, the important thing about a chart is its footprint. So when you do a restriction, you restrict to a subset. We write this chart we could write as K, and we write it as K restricted to V, where V is an open subset in the footprint. So we're thinking of restricting the chart on the footprint. And what this is going to consist of is another tuple. And all the data, apart from U, is just sort of identified with the same data. Well, it's a restriction of psi. But all this data is the same. And U prime is going to be inside U. It's open. And it has a property that U prime intersect S inverse of 0 is precisely psi inverse of V. So it's just a neighborhood. I mean, it's sort of the obvious definition. It's just the neighborhood of the footprint. But I would say that one of the differences between our approach and the approach of Fukaya and Ono is that we're always working, we don't work with germs. We work with things which have precise domains. And then, of course, there's another choice of domain, but that's something that's always there. Okay? Do you want me to rewrite that as, could you remember what I
missed what your prime was.
I missed what your prime was. U prime has an important property that U prime intersect S inverse of 0 is the pullback of V.
But it does not define the prime initially.
No, that's the whole point. But we have it as part of the data.
In fact, once you have isotropy, it might not exist.
Well, let's not talk. We're not talking about isotropy. Let's not do that.
What do you mean the part of the data?
Well, I mean that when we take, say, K restricted to V, normally when you do a restriction map, you think, well, there's sort of a unique restriction. But here there is not a unique restriction because we've got U prime, E, S, and psi. All these are sort of given by restriction. But U prime is, you have to choose U prime. When you're making, well, so V is just some subset of F. We fix V. And when you fix V, there's a choice of U prime, right? So it's not like a germ where we forget about that choice. We actually say a restriction, you have to make that choice, right? So that's where one of the ways in which we have a difference with Fukai and Ono because they seem to, I think they just take germs. And so that's a definition of restriction. And then we want to say what a coordinate change is. And so here you can have a picture. We've got, some set. So here's X, and it's got we've got some bit of a chart over. This is the footprint F, and then we've got another footprint F prime, and we've got a chart K for F and K prime for F prime, and we want to define a restriction over the common bit over this intersection, right? F intersect F prime. And we want to then define a coordinate change. Now normally if K is sitting over F and K prime is sitting over F prime, you don't have a coordinate change from K directly to K prime. What you do is you build something over the intersection and you have a map of each of those into that. So that's sort of one of the thing which well, this is horrible notation. Actually, well, I don't want to write some of the charts. Let me just say the idea is that you build something over here which has a recipient, because typically, you see this. Typically, you've chosen some obstruction bundle here and another obstruction bundle here, and there's not much relationship between them, so that you can't expect to map one thing to another thing. What you can hope, what we do arrange eventually is that the obstruction bundle here and the obstruction bundle here are so different that you can take their direct sum. So they're sort of sitting inside a common space, and it makes sense to take their direct sum. So you can build a chart here with the obstruction bundle E plus E prime. And the footprint is F intersect F prime. Now, when we make a Kuranishi structure, a Kuranishi structure, we've got our space X, and we're going to cover it with a bunch of these charts. And they could overlap many times. So we're going to have Ki for I going from 1 to n are our basic charts. And their footprints, the union of the footprints, Fi is going to equal X, right? So that you just take, around every point you can build a basic chart. We've got a compact space X, so we can pick out a finite number of them whose footprints cover X. So that's sort of the basic data. And then we have to explain how to put them together. And so then we get, a set IK, which is the set of all subsets I sitting inside 1 through n, with the property that the Fi, big S capital I, is always going to mean the intersection of the Fi's. That's non-empty. So we look at the non-empty intersections, and then we're going to build charts Ki, and for I and with I and Ik, and their footprints are going to be the Fi, and these are going to be the recipients of the coordinate changes. So, for example, we'd have a coordinate change from K1 to K12, right, and so on. So we're going to have, in fact, in general, we're going to have coordinate changes from Ki to Kj when I is contained in J. That's what we call our transition data. It's a whole bunch of compatible functors. Well, I'll explain what sense you can think they're functors, but a whole bunch of compatible coordinate changes between these things. And so you see, when you over an overlap of two things, your bundle is just a sum. Over an overlap of three things, it would be a sum of three things, and so on. So the bundle is going to get bigger, typically. But if we just want to define one coordinate change, so let me tell you what a coordinate change is. And let me use the notation from Ki to Kj. And this one has got footprint Fi, and this one has footprint Fj. And in fact, if J is bigger than I, then this is the intersection of more sets than that. And so we're actually going to have Fi is going to contain Fj.
Is this like supposed to be an intersection of this K big I? Intersection?
No, that's a chart that we're going to form by some construction. I haven't exactly explained to you how we're going to do that yet, but it's just.
You haven't said what K big I is yet.
I haven't explained what these are. These are something we're going to have to.
K big I is a Kuranishi chart with footprint F capital I.
Yeah, so we know what's happening on the footprint level. We're just intersecting.
But you haven't explained yet how you get to this.
I haven't exactly explained how to do this. No.
That's going to be my job tomorrow.
Well, I will tell you more about this. Yeah, no, Yeah, I understand. I have not explained. I'm just giving you an abstract definition of what a Kuranishi, what a coordinate change is from one chart to another chart. I'm using this notation because that's going to be what's going to be relevant later. So I'm labeling this one as K big I and this one K big J. And I'm thinking that, so they've got footprints Fi and Fj, and these Fs are intersections. And therefore, we do know that Fi is actually bigger than Fj. Right? And actually, we will also have the situation, this is not true for all charts, but in the charts we're going to look at, EI is actually going to be a sum. We're going to have each of these has got obstruction bundles E little I, and the E big I's are going to be just the sum of the relevant E little I's. That's what it's going to be. Well, the sections are always given by the del bar operator. I haven't said what a coordinate change is. Right. It's just some section, right? Well, Ki. Yes, but look, it's an abstract chart given this name. I'm saying these are given. I'm saying what is a coordinate change? What do I mean by a coordinate change from one to the other? I've told you what a basic chart is. And Katrine actually gave you an idea of how you might construct it. I'm saying when we're trying to build a Kuranishi structure on a space, we have to glue our basic charts together. We have a K1 and we have a K2. And in general, we have to have an intermediate object, a bigger object in which to put them both into. We can't, given that and that, we can't map one to the other. We build this bigger object. And then I'm trying to explain what does it mean to say that this maps to a bigger object. Before I have to explain what I mean by mapping one chart to another one. What kind of maps are we allowing? So these are just tuples. These are tuples. I told you they're tuples of 4 things. Okay?
So the structure of the definition is a Kuranishi structure is a collection of 55 objects satisfying the
Right.
following conditions.
Right.
So I'm trying to understand sort of this Ki, are this like among these 55 objects got.
Well, that is another Kuranishi chart. It's a Kuranishi chart. They're given. A Kuranishi structure is going to be, if you actually want to know what it is, it's a collection of these basic charts together with a collection of these transition functions. So you have to give those basic charts, plus the coordinate transformations that I haven't yet defined, and then they're meant to satisfy some compatibility condition. Okay?
K capital I are part of the data.
They're part of the data. They're part of the data. Well, this is a finite set, finite number of basic charts. So there's a finite number of index sets here. Everything is finite.
So what is the SN side? They are all fixed or what?
Well, no, that's all part of the data. That's all part of the data. Each chart has its own data.
In Ki capital,
Right. This one.
your footprints and vector bundles come from your basic chart.
Well,
But sections don't.
Okay, the footprints do always come from the basic charts. The vector bundles don't have to. The vector bundles could be arbitrary. For a definition of an arbitrary Kuranishi structure, the vector bundles could be arbitrary. I'm telling you in practice for the useful ones, which we call additive Kuranishi structures, they come from those of the basic charts. Okay? But before you impose the additivity condition, they could be anything you want. But I do have to tell you what a coordinate change is and explain to you what the choices are. So a coordinate change, you first of all have to do a restriction. You have to restrict Ki to the intersection of Fi intersect Fj, which happens in the particular case I'm looking at to be Fj, but it doesn't have to be. So we do this restriction. So this involves a choice of domain. So the domain of this is what we call Uij. So that is a subset of Ui. It's a subset of this domain. Everything else in this restriction is given except what that domain is. But we have to choose that. So a basis uses that restriction. And then you have a map here. You have an inclusion there, which is given by this functor. Well, why do I say functor or F hat? Well, we can think of, in this particular case, if there's no isotropy, thinking of you can think of a Kuranishi chart as given its domain is just an open subset with only identity morphisms. It's a very trivial kind of category. The bundle is also a trivial kind of category. It's just the open sets are U times E and identity morphisms. Of course, if you had local groups acting, you'd have some morphisms. But here we don't have morphisms. Then S is a map, but you can also think of it as a functor. And psi is also you can think of it as a map, or you could think of it X as another one of these trivial categories with objects X and just identity morphisms and map down. Okay, so you could, and then, but if you think of this as a bunch sort of given functorially, then the point is to say this just means that this commutes with everything. It has all the naturality properties with respect to the maps that you'd expect, right? It intertwines everything. So what does phi consist of? Well, most importantly, we have to say what phi ij does. Let's call it little phi ij. That is a map from this domain to that domain. And then it's covered. We also have a map phi hat ij, which is a map from the obstruction bundle EI to EJ. And this we want to be an injective. This is just a linear map, just mapping this in there as a subspace. And then we want everything to commute, right? So we want a commutative diagram, Uij to Uj, Uij cross EI to EJ. And so we've got some maps here, just a product map, right? We've got the sections here, and we want this diagram is meant to commute. This we can call SI, that we can call SJ. And if this commutes, then it clearly takes footprint to footprint. Right.
Is J still greater than I? Or is it required or not? Yes.
Well, if you're doing it abstractly, these are just abstract names. If we're doing it, and so then it doesn't make any sense. But if we're doing it in the case for a Kuranishi chart, then we will have that condition. So you can restrict it down for a Kuranishi structure. We'll be only looking at cases where I is contained in J.
So the maps phi ij and hat, they are injected, both of them? Or?
They're both, okay, so this one is just an injective linear map. This one I have to say a bit more about. Okay, but it is actually also injective. But one of the things I forgot to tell you about Kuranishi structure is what the dimension of a Kuranishi structure is. So the dimension of a Kuranishi structure is the index of the problem. In other words, it's the dimension of what the zero section would be if it were regular. So the dimension of this is just the dimension of U minus the dimension of E. So, if S were a regular section, then the zero set would be as manifold of that dimension. And so when you do a coordinate change, one of the conditions is that these things have the same dimension. So what that means is that when you're looking at this map, it's definitely not, it doesn't have image and open set, because, if the dimension is D, this has got dimension D plus the dimension of E, and this has got dimension of D plus the dimension of EJ, and the obstruction bundle may go up. This could definitely be an inclusion, because typically this is going to be a sum. You see, in this case, we're taking two charts with unrelated obstruction bundles. Here we're going to put E1 plus E2 in there, or E1 plus E prime. So then if we're mapping E into that, it's definitely injective, not surjective. And that means that this domain is going to be an embedding, a smooth embedding, but it's actually going to have to satisfy more conditions. So let me get a little bit more blackboard for that. So if we have a coordinate change from Ki to Kj, phi hats are just linear maps, linear, and everything's meant to commute, so that whatever is appropriate. So we have our map little phi ij is the map on domain, goes from uij to uj. Actually, the image of phi, well, the first thing I want to say is that the dimension of ki is equal to the dimension of kj. The second thing I want to say is that phi is a smooth embedding. And then what we need, though, because it's got an open domain, we need its image to be somehow controlled. So its image has to have a normal bundle, but we really what we want this is sort of the tangent bundle condition, that if you, we actually had this written down nicely, so let me write it down in the same way in a paper, that if you look at phi hat of EI and you add to it dsj hat of V, so for all, if we look at a point V in the image, so this is in the image of phi j. So for all those points, we need this to equal EJ. So what that means is that we've got this is our image of phi ij. This map from phi hat is typically not surjective. So we're saying that the section in these transverse directions, if you look at the derivative of the sections in these transverse directions, that has to cover the quotient. So ds hat j, if you like, restricted to the normal bundle to the image uij, that maps this normal bundle. So this is surjective to the quotient. So all the extra, because our bundle EJ is typically bigger dimensional than the bundle EI when it maps in, and all those extra directions are covered by the section, the derivative of the section in those extra dimensions. Well, this was what they assumed. This is in the recent. I know we're not claiming this is new. In the very first version. I know it is. I'm not claiming it's new. It's not in FO, but they corrected it. It's not in FO, but they realized they assumed that there was an isomorphism, but then they realized that they had to make it sort of the isomorphism had to be given by ds, because otherwise it didn't work. Yeah, yeah. I know. I mean, I know this is, and we're not claiming. The only thing that I would say is different from FO is our emphasis on taking everything defined with definite domains rather than being defined on the germ level. Right. That, well, but well, I think the may. Well, anyway, we could talk about that later. Let me just tell you, we were going a slightly different route from looking at germs, and we were looking at it with these definite domains.
And another point is this construction about this Ki, Kj, and so on. I think this is what they call good coordinate chart.
This is a good coordinate chart, but they never show. I mean, that's where we basically started from their definition of a good coordinate chart, because they never showed, or at least gave a very convincing argument that from the definition of what they called a Kuranishi structure, you could actually build a good coordinate chart. So we just decided to start off with a definition of a good coordinate chart, right? So that's what we did, and we formalized that. But it's certainly very close to what they did. I mean, it's nothing hugely new. Yeah. No, phi hat is just a linear. We've trivialized everything, and that just is a map. So it respects the trivialization. Right. Oh, why has that got a hat? To tell you the truth, I'm not quite sure. I don't think it should have a hat. Yeah. Okay. Yes, I was just copying. I was copying something which had a hat in it, but I think actually what I meant, it shouldn't have had a hat. Okay, and then, so then there's only one other thing to, we have to look at composites. Suppose you've got a map from Ki to Kj, and you've got another coordinate transformation to Kk. So this is phi ij, and this is phi jk. So then you can obviously form a composite. Psi. Well, I missed out. The point is that, you see, if we have this commuting diagram that it intertwines, this map phi ij is going to take S inverse I inverse of 0. That's certainly going to be contained in Sj inverse of 0. Yes, and then I should have said, yes, I shouldn't have missed this out. This is an important bit of the definition, that you've got these footprint maps. This is going to Fi. This is going to Fi intersect Fj. There's a natural inclusion there, and everything is meant to be compatible. So it's meant to restrict on the footprints to the obvious inclusion, right? So that's what I meant by the functorial properties, and I didn't spell it out. But you're right. It has to extend the obvious thing, and the only point really is that, I mean, when you're doing this and in the constructions, the only choice you really have here, because everything we do is fairly canonical, the only choice you really have is a choice of what that domain is. Once you've chosen that domain, you basically know what the inclusion phi hat is. You know what phi ij has to be. So everything is sort of, as I say, everything is basically canonical. You just have to check that it satisfies the right conditions. But there is a choice, which is that choice of domain, because you're doing this restriction. And so when we talk about the cocycle condition, you see, when we have three charts like that, we have a map that just goes from I to K, and we have this intermediate thing. And the domain of this is going to be, it's the domain of this composite is just the domain on which the things make sense. So it's Uij intersect phi ij inverse of Ujk. That's sort of the biggest domain on which you can define this map, and you can easily prove then you do get a coordinate change. In other words, that these conditions I put on this thing are going to be okay. So you have a coordinate change. You also have another coordinate change, and what we want to do here is to build a category. So we need to know that if each morphism here and here are going to represent morphisms in our category, we want to be able to form composites. So our co-cycle condition is that that's contained in UK, and that's called the co-cycle condition. We're not necessarily assuming equality, but just inclusion, so that you do know that composites are defined. And so then, what is a Kuranishi structure? So a Kuranishi structure is basically what I've indicated to you, which we're going to call K, is, well, it's a collection of these basic charts, which give a footprint covering, together with all these coordinate changes. For whenever I is contained in J, and they both have non-empty footprint, so that the co-cycle condition holds. And then, given that, you can build a category. Okay. Yeah. Well, well, if you're giving coordinate changes, you have to give the domains and the targets of the coordinate changes, right? I mean. Well, they're all part of, they're in each coordinate chart. And when I say I have a coordinate change, it's meant to respect all the S and the footprint. So I did. So then you can write this down. You get a category. Well, you get a bunch of categories. You get the domain category, B of K, which is a category with the objects are just a disjoint union of all the UIs. And the morphisms are given by, well, you have the identity morphisms. Well, you can think of an object as a pair IX, and you have a map from IX to IY. If X, sorry, to JY. And X is going to have to sit in UIJ, and Y is going to have to be phi IJ of X. So the morphisms, those are, well, I is less than J, I is included in J, right. And so your morphisms, the space of morphisms is going to be the disjoint union of all pairings like this of the domains where we put UII equal to UI. Yeah, so the domain, so for each pair ij, you have a component in the morphism space where the domain is uij. So this represents the set of morphisms between an object here and an object there, right? So I mean, if you think of abstractly of what the morphisms is, you have for each pair ij with I contained in j, I possibly equal to j, we have a unique morphism. We have a morphism. Well, the objects consist of all these elements ui. Yeah, so we have say a u1, and we have a u2, u12 say, which it might typically, well, it could be like that. And then we have a subset in here. Sorry.
Are objects these open sets or points?
Objects are points. Objects are all the points in here. I mean, it's a topological category. So each point in here, I mean, so we write a typical object as I. The objects are points, right? Well, no, that's the whole point. I mean, one of the points, it certainly doesn't have to be Hausdorff for this. But I mean, we're just trying to say what we get. This is we're just putting, our definition was designed so that this would be a category. So that's why we had the co-cycle condition. Yeah.
Backtrack a bit for a second. On the left top corner, K is this collection of KIs. You actually
And
that.
that.
But about KIs, you actually want to include all multi-indices too there, right? Not just.
Well, it depends how you write it. I mean, you certainly could. You certainly could. Yeah. Yeah.
So I think the construction of the Coronation structure for Gromov-Witten invariants will very crucially involve making by hand these sum charts.
I'm just asking about.
Yes. Okay. Listen. It's look. By writing this, look, Victor. By writing this, I meant the KIs to be given. Okay. I didn't write it here just because I hate writing things on this board, right? But it consists of that, and that, right? You have all these charts and you have these things and they satisfy the co-cycle condition. And then you build a category whose object is a union of all the domains, all the U big I's, which are all the domains of all these charts. I mean, you're right, it may be better to write it down like that. And then the morphisms are given by the transition functions, okay? And the point is this is a category, but it's not, and it's a category where there's at most one morphism between each object. But I do want to point out that we don't invert the morphisms. It's not the same as a groupoid. So in other words, if we have, you see, we have a U1 and we have some open set here, which we're calling U1, 1, 2, which gets identified with some open set there, right? But if we have a sort of this bit of a zero set here and it goes to some zero set there. But the thing is, if we have U2 going in there, if we went up there and down there, the intersection of the images from U1, U2 and these images typically is just in X. They just intersect in X. And therefore, the morphisms, the composite morphisms going from here to here, the domain would be something homeomorphic to X. It would not be an open subset. It would be homeomorphic to an open subset of X. Because the way we have it, our transversality conditions, is that this image goes into, you see, the image of phi 1, 1, 2 is contained in the image phi hat of E1, and the image from phi 2 is contained in phi hat of E2, and typically these two things sitting inside, we've got E1, 2 is typically going to be isomorphic to the direct sum of these things. So the only thing which is in, I mean to say Sj inverse of that, S12 inverse of that. And this is sitting inside S12 inverse of that. In other words, just the equivariance conditions with respect to S tell you that anything that comes from chart 1, its S has got to map into the image of E1. Anything coming from chart 2 has got to map into the inverse image of the thing E2. This is the direct sum, so the intersection of those two things is only at 0. And therefore, the only time you could start in 1, go to 2, and go back is if you started on the image of the 0 set. And that may be horrible. And since we wanted to keep ourselves in the realm of categories where we have nice domains, you know, where our categories are, these domains are open subsets of Euclidean space, we don't put in all the inverse morphisms. And so that makes it more complicated. I mean, you think you're working in a sort of like a groupoid kind of category, but Hausdorffness is a real problem, for example. Anyway, that's the definition. And
So a good Kuranishi structure in your sense might be one where the orbits, they identify points by morphisms, but not the whole space.
well, that's not what I would call a good one, but I mean, it's certainly, from the definitions I've given you now, that could definitely happen.
But when you ultimately do something,
Ultimately, I will state, what I'll do now is give you the theorems. I don't know how much time I'm going to have. I was trying to give you the definitions, which would tell you that we have a theorem which took us a long time to prove, which tells you that if you put these assumptions on the Kuranishi structure, you can arrange to get a Hausdorff quotient. So I thought I'd like to state that theorem now. I might want to, I could prove it for you tomorrow. Well, let me just tell you what we're going to do. So we have a similar thing for the bundles, which I won't bother to write out. So then we have a space K, which is going to be made from the objects of this category BK. I was going to write it down here. I think it's an E. Okay. Right? It's exactly the same thing, except you multiply everything with E's appropriately. And the objects are going to be the disjoint union of the UI times the EI. And so that you've got I and X and you've got E or something, right? Triples. Oh yeah, they're all points, right? It's a topological category, right? So I mean, I was saying that, the category corresponding to X consists of the points of X with identity morphisms, right? But I wanted to have objects categories where the objects are open subsets of Euclidean space, so they're sort of manageable. And then we can define the realization of a category, which is you just take all the objects and you quotient out by the equivalence relation, where you say two things are equivalent if there's, it's the equivalence relation generated by the morphism. So if there's some combination of morphisms sort of getting from one to the other. But it won't be actual morphisms because we're not allowed, because we're not allowed to invert morphisms. So it will have to be the equivalence relation. This is generated by the morphisms. And then go there, back, there, back.
So I go from Y to an X and Z comes to the X.
Exactly. And so then we have this map here, which is just the fiber over each point is a vector space, but the dimensions change. We have a section which is well defined because everything commutes with that. We again have a footprint map from S0 into X. And this is now actually bijective. And in fact, you can prove that however bad your category is, that because everything was sort of compatible over X, that this is bijective, it's a homeomorphism. If you give this a quotient topology, right? It's a quotient space with a quotient topology. It's the only thing you could. And you can prove that it still has a nice zero set, which is what you want. But you want more than that, because we have also a projection map, pi k, say, from UI to UI with its quotient thing sitting inside k. This does not actually have to be either injective or a homeomorphism to its image. I mean, this could be horrible in general if you make no assumptions. We would like this. We want this to be a homeomorphism onto its image. And we also, that's one thing we want all those maps to be homeomorphisms onto their images, which the good thing would that be is then if we're trying to work on this space here, we could just pull back to a local chart and work in a local chart and transfer it back, right? So we want that property. And then the second property is we want K to be Hausdorff, this space here to be Hausdorff. And let me just explicitly say why that is. We've got this sort of generalized bundle. And we've got X sitting inside here with some inclusion, which is a zero set of S. What ideally we'd like to be able to do is say, okay, this is meant to be a finite, this is sort of a virtual neighborhood of X. We'd like to be able to perturb S to some section big S. So that's a perturbation, which is smooth and transverse to 0. And then we'd like to say that, you know, S inverse of 0 is a smooth manifold. Well, everything was smooth. I mean, all our maps were C infinity except for the footprint map. Well, this is just quotienting out. We're quotienting out by a bunch of smooth things, right? Yeah. And when I say this is a homeomorphism, I mean, when we say smooth, you say we've just got, this is just a topological space, I suppose, here. But it has these local charts, and we can ask it to be smooth in a local chart, and all our transition things are smooth. So we can ask to say smooth means that in each local chart it's smooth. So and
smooth by default, but possibly non-Hausdorff.
It's smooth by, yeah, this thing could definitely be non-Hausdorff. And why I want it to be Hausdorff is I want this to have a fundamental cycle. I want it to be compact, which is not so difficult to arrange because you started off with something compact here, and you can say, you can sort of compactify this, so you can make this live inside the interior. So you can sort of make a construction. You can close that and make this compact, sitting in some other Kuranishi chart. I mean, actually, what you do is you start off with this one and shrink it down, so that you have it compact inside something. So that then you can make sure that S is very close to this big perturbation is very close to the 0 set to get compactness. So the compactness is not the problem. The smoothness is not really the problem. The difficulty is that if you can have compact smooth manifolds which sort of look like this, which don't, if you don't put weights on these two branches, you won't have a fundamental cycle. And we have no way of putting weights on anything. We don't have any isotropy. If you have isotropy, then as Helmut pointed out earlier, the right object isn't for your homology class is not a smooth manifold, but some kind of weighted, locally smooth manifold. But if it's if we don't have any isotropy, there's no way to put on weights. We certainly don't want this to happen, and this could definitely happen in a non-Hausdorff space. And we could definitely have non-Hausdorff spaces. I mean, just to give you an example, we could have a situation like this, where this is a 0 set. This is our chart U1, this is our chart U2, and this is our chart U12. And so then we glue, you know, all these points are identified with all the, so we just sort of glue those. But everything was open, remember? So we have a point here on the boundary, which is, these are different points. And yet they have no Hausdorff neighborhood. You see, if you just glue on sort of arbitrary open sets, which is what we're doing, and we can't say, okay, we want this image back. We can't. See, we have a morphism that way, and we have a morphism that way. We don't have a morphism directly here to here. So we can't compare this domain with that domain. We have to always go forward. I mean, at least in our maps, we go forward. So somehow we have to express, I mean, basically what you want to do is cut that one away from this or something. You want to prune the domains and make it Hausdorff. But you have to find a language in which to say that. So let me just. Yes, I know. I mean, this is a. Well, the point is that Fukai and Ono never worried, as far as I can make out, about this Hausdorff property. They made all these local identifications, and they just, well, I mean, anyway, let me just explain what I'm doing. I'm trying to make this abstract construction and tell you how you get a Hausdorff quotient from our construction. Because, you know, another way you could deal with it, which is done in polyfold theory, is to say, well, all our domains are actually going to be sitting inside a space of stable maps. That is Hausdorff. So let's use the identifications coming from the space of stable maps. We identify things if they have the same image. but you know your identity. You know, you've proven that the space of stable maps has a nice polyfold structure. Everything is smooth there. That's no problem. For us, we have huge problems in putting on smooth structures on an infinite dimensional space. So we wanted to have everything intrinsic. We have, you know, K is given by these open sets, and that's all we know about. The only things we know about are the morphisms we define and control. We can prove those ones are smooth. We can't have any other abstract maps which are given by something we don't quite know, which allow us to identify those 2 points, for example. We can't just say, okay, there's a way of identifying those in some stable map space, because we don't know about smoothness there. So we have to have an intrinsic way of getting something that's Hausdorff. And the way we do that is to make a definition. Well, we have one definition about K being additive. And K being additive just means that EI is isomorphic to the sum of the EIs, compatibly with all the, so the inclusions are just the sort of obvious inclusions. We actually have an idea of a weak Kuranishi structure, and this is where we relax the cocycle condition. The cocycle condition was telling you that the domain, if you looked at a composite, that the domain of that composite was actually sitting inside the domain of the direct map going from done to there, which is actually quite hard to arrange if you think about it, because you're just constructing these things. You know, you construct one and the other, and you don't really know what their domains are. So what the cocycle is condition is, this is equal wherever they're both defined. Which will mean that it's equal on some neighborhood of the footprint, I mean, the way it goes. So that's enough. And then we have the idea of a tame Kuranishi structure, which is where we put pretty strong conditions. Let's see if I did write them down somewhere. Yeah, so a tame Kuranishi structure satisfies the following conditions: that Uij intersect Uik is equal to Uij union K. So that's talking about if we're in Ui, and then we have all this set of family of sets. These are the ones which can be mapped to Uj, these are the ones that can be mapped to Uk, and we're saying that if a point can be mapped both to Uj and Uk can be mapped to the union of them. Right? So that's a compatibility condition. These are actually equal. And the second condition is that phi ij of Uik is equal to Ujk intersect S inverse of Jei. And this is telling you that it's telling you something about the image. We're saying, suppose this is a transition map which goes from I to J. Yeah, I think this is for I contained in J contained in K. And it's telling you that if you look at the part of Ui which actually gets mapped all the way to K, that's what Uik is, and we look at the image of that in there, then we can identify it. We know exactly what it is. It can also be mapped to K from here, and it's the whole of the things that can be mapped to K that are sort of identified by which actually correspond to the obstruction bundle EI. So these two things give you a huge amount of control over these identification maps. So there's one thing you can prove is that if you have a weak tame, so our theorems, what's the time? I have to stop, so this is good. Theorem A is, or lemma is, if you like. Lemma is that a weak tame Kuranishi structure is a Kuranishi structure. So you can get rid of the weakness. In other words, the weakness was just saying that this is what we call the overlap condition, equal wherever defined. If it's also tame, in fact, the domains of these two things happen to be equal, so that's even stronger. And then the theorem is that every weak additive K structure has a shrinking such that is tame, and the additivity. So what you mean by a shrinking is essentially what you'd imagine. I don't have time to write it down formally, but our data consists of these charts, Ki and the Ki and all these coordinate changes. A shrinking means you slightly shrink the footprints to some precompact open subset. You slightly shrink all the footprints, but keeping the same intersection pattern. And then you shrink all the shrink these correspondingly, and then you restrict all. You choose some restricted domain. So basically, the point of a shrinking. The point of this theorem is, you can choose any shrinking of the footprints to make them precompact. The whole point is to figure out what are the new domains. You need to find a consistent set of new domains which satisfy these conditions. What do we do? Oh, I haven't worked it out. In fact, it wouldn't work here because it's not additive. Because if it's additive, when you go, you see our transition charts would never go from U1 and U12 having the same dimension.
Oh, right.
It would always go up a dimension. So I haven't even drawn the right picture for you. Anyway, so this requires a bit of proof, but somehow, once you have that, there's also a cobordism theory, right? We're trying to define these uniquely up to cobordism. So you have to say what you mean by two things being cobordant, which is basically what you would imagine. You have x times I, you have some Kuranishi structure, K01, which sort of sits over that and restricts to a product at one end and a product at the other end. So you have a Kuranishi structure here, you have a Kuranishi structure there. You can take their products over little neighborhoods, which just means that you multiply all the charts by some little interval in 0, 1. And then you can put anything in the middle here to make it a Kuranishi chart, and that's what we'd say a cobordism is. And then we prove that this shrinking is unique up to cobordism. And so that means once you start off with a weak, why we've got the weaken is that is what you can construct. You can basically take any family of covering basic charts, perturb them slightly to make them additive, because you have to make your obstruction bundles disjoint, and they will sort of naturally give you a weak additive structure. So that's what you can easily construct. And then we do the shrinking, which is a little bit complicated, but basically just ordering all choices in some very important way, but using the additivity to help you order the choices. And then you get this tame, and then, oh yes, and I forgot to say the important thing, a tame one, if K is tame and additive, oh yes, there's another important theorem, that implies that K is Hausdorff. I forgot to say that. It implies that K is Hausdorff and that pi K from Ui into it is a homeomorphism to its image. So the tame ones are the good ones. That they have this nice, they have a nice image, and then that gives you something you can work with, right? And you have to, well, you can imagine you have to define sections and whatever. But I thought perhaps next time, well, actually, to prove that tame and additive is enough for Hausdorff is not trivial. To construct this shrinking is not trivial. So I can explain that next time, unless people say they really want some other aspect of it. There's another aspect, how do you construct the sections, but I think you can imagine that's more obvious. Anyway, I think I should stop now, and I'll continue tomorrow. It was like it's almost more or less what they assumed a good coordinate atlas would be.
So let's assume we have a good coordinate system in any sense, which means we have this local finite dimensional reductions, and if some ordering is satisfied, we have a map interface.
Right.
So I can definitely define a topological space by identifying points by the equivalence relation of this inclusion if I have a good coordinate system.
Yeah, that's what we're doing when we're getting this K.
But I think whatever definition of a Kuranishi structure, if you have some you must have relations between the things. You will have
Yeah.
the original space X embedded to this.
Yeah, this
But
contains.
now, if the space, the group space together is not Hausdorff, and you make a perturbation theory, I think you could get this branched manifold.
Exactly, that's
and
what I was saying.
If you triangulate them, they are not even they're not even.
Well, that's exactly what I was saying up there in red, that you had to have the Hausdorff property in order for the zero section.
So that means then there's no way that you get a virtual fundamental class because it wouldn't be.
This is because you want to construct this fundamental cycle on the Kuranishi space itself. But the purpose of the Fukai and Ono and Joyce's approach is not that. What they're going to do is trying to construct a singular homology theory in the target manifold. So you don't need to worry about this Hausdorff. You don't worry about it. So the only thing in the Hausdorff is in the target, not in the this original Kuranishi space is already metroidal. It's already the Hausdorff space.
But how do you know that you get a cycle if you can't? You need a cycle. You see, you can because you could have.
The cycle on the Kuranishi space
No, forget Kuranishi, but still, but to construct the image, you have to make sure
Was
it's
the
a cycle.
image going to be
So
Hausdorff?
now this condition here would guarantee what you construct is a cycle. Of course, you can construct in the image, but then you have to compare that thing is actually a cycle. But the only information you have is the Kuranishi space.
You have to. You see.
The question is, how is the thing that you construct in the target ever going to be Hausdorff?
Well, no, but Katrine, it will be Hausdorff because the target is Hausdorff. You're back, but you need to know.
You make a chain. I mean, you make a chain. So you need a triangulation. Right?
Yes, I know, but you have to look. You see, the difficulty is
It's a map from a CW complex.
you have to. Well, you have to. But you have to know what the boundary is, and if you can have some branching if you can have branching in your domain, you could have something which looks perfectly nice, looking like that in the domain, which doesn't carry a fundamental class because this is sort of a one, and these two things are half each because it's branched. And if you have a way, yes, but you don't. Yes, but they do that using the isotropy group, and we don't have an isotropy group, so we should not have branching. The thing is, if you have an isotropy group, then of course you do get a branched object, and we would get a branched object. But
the difference is if you're trying to construct a fundamental cycle on the Kuranishi spaces.
well, anyway, I think this is a gap in what they do. We could look more carefully and see whether it really is, but from the way we're trying to do it, we want to make absolutely certain that we have a cycle which we're mapping in. And our cycle that we're mapping in is represented by this manifold. And I think I think there are just inevitable Hausdorff issues of whether the quotient space is Hausdorff.
No, I think you're trying to prove a much more stronger theorem than what they're trying to do.
Well, that may be. I mean,
I just spent a week trying to read Fukaya Uno and trying to understand how they even get a compact perturbation space. And I think everybody should go and do the exercise of looking at Fukaya Uno, looking how they make the triangulation. So what happens there is that they construct their sections chart by chart. And in every single chart, they choose an epsilon, which, for the simplest possible example of